Log on, tune in, find out. Another good idea from Cambridge.
Okay, so I'd like to start out by thanking the organizers for inviting me. This is an extremely pleasant place to work and lots of stimulating conversations, so it's very nice to be here. Okay, so what I'm going to talk about is joint work with various people. I'm going to talk about some stuff in the discrete domain. That's going to be the bulk of the talk. And then towards the end, I might say a little bit about continuous settings. So the discrete work is joint with Adam Marcus and Prasad Tetali, Adam at Yale and Prasad at Georgia Tech, and the continuous work is joint with Sergey Bobkov at Minnesota. So to outline my talk, I'm going to start out with some motivation for Rusha type sumset calculus and present two illustrative inequalities, one for entropy and one for cardinality, that will serve as just as introductions basically. And then I will describe some inequalities in a more general setting for so-called partition determined functions, which I need to define. And I will discuss as applications inequalities of Plunek-Rusha type for abelian groups, as well as an application to non-abelian groups. And then, as I said, time permitting, some continuous analogs. So just to give some context, which probably is not needed, but so the canonical example in which we study sumsets in groups is the study of additive structure in the integers, not just multiplicative structure. But more generally, one might want to study a point of view which has been developed by people here, among others, the study of approximate subgroups. And there have been major developments in recent years, such as the Green-Tau theorem on the existence of arbitrarily long arithmetic progressions in the primes and so on. So just to fix some terminology, we will call sumsets basically sums of the form. We will write them as A plus B. These are all sums of pairs of elements taken from A and B respectively. And the same notation is used even if A and B are not finite sets. But okay, so a sumset inequality is going to be any inequality for cardinalities of sumsets under a variety of conditions, and usually we have more than two. We have a number of sets that we are considering. So these sumset inequalities are an important collection of tools in additive combinatorics, and there are many of them, like the Cauchy-Davenport inequality, the Plunek-Rusha inequalities, the Balog-Chemereddy-Gowers theorem, and so on. And one example of a place where they find utility is in proofs of Feynman's theorem, which is a fundamental structural result in additive combinatorics. Okay, so let me also mention with an eye towards the continuous analogs that I'll touch upon later, that there are analogies between geometry of sets in Rn and geometry of discrete sets, of course, well known. So for example, the Brun-Minkowski inequality talks about the superadditivity of the volume to the 1 over d functional for Borel sets in Rd, whereas the Cauchy-Davenport inequality, for example, I mean, just looking at it for the case of the integers, says some sort of almost superadditivity for the cardinalities of some sets. Okay, so our focus is not going to be on lower bounds like Brun-Minkowski and Cauchy-Davenport. Rather, it's going to be on upper bounds for both discrete and continuous settings. And also, it's not going to be so much on structural results, that is Feynman type results, which tell you something about the structure of sets under conditions involving some set cardinalities and so on. But it is going to be an effort to develop some kind of calculus for getting bounds on cardinalities of or entropies of cardinalities of some sets or entropies of random variables, as we'll see. And the key tool for all of the results that we are going to describe is going to be to use entropy ideas, and that's also going to make for compact proofs and so on. Okay, so let me just introduce some more terminology. So for a discrete random element x with a probability mass function p, so x takes values, say little x with probability p of little x. The entropy of x, which is really a bad notation, but it's standard now. It's really, the entropy is a function only of the probability mass function p, and that's the expected value of minus log the probability of x, or in other words, you can write that as the sum of minus the probabilities, the log the probabilities. Okay, so I had these definitions of conditional entropy and so on in there, but you can ignore that. If we need it, we'll come back to it. I'm going to try and avoid going into proofs, although if there are questions, I'll come back and explain some of those things. So two useful facts that I want to mention right away. The first is that in discrete settings, the entropy is non-negative. That's one. And the second is that the entropy, the joint entropy, satisfies a very important property called sub. XYZ together is also a discrete random variable that has some joint distribution, and this is the entropy of that joint distribution. Okay, so the entropy of the joint distribution of x, y, and z and z, I should say, plus the entropy of x is bounded from above by the entropy of x and y plus the entropy of x and z. The point here is that the entropy is not additive, right? The entropy is sub-additive. The entropy is a measure of information or randomness, and the information in x and y together may be less than the information in x plus the information in y because of dependence between x and y. Okay, so this submodularity is a fundamental inequality. So there is a natural connection between entropy and combinatorics, which arises from the fact that for a finite set A, the entropy of the uniform distribution on A is the log of the cardinality, and that's the maximum entropy of any distribution supported on A. So this, not surprisingly, this means that one can use things about entropy to prove things about cardinalities, and this idea has been used from long back. I think the earliest papers were probably due to Nicholas Pippenger, but more well known is a paper of Chung, Graham, Frankel, and Shearer in 1986, work on intersection families, and then a proof of Bregman's theorem by Radhakrishnan using entropy. And then there have been applications to various counting problems, including things like counting independent sets and graphs and so on. But the applications of entropy in additive combinatorics seem to have been developed much more recently. The pioneer here was Imre Ruscha, and in spite of the fact that the date looks like 2009, I believe Ruscha was developing these ideas well before that. And there's also there are some unpublished notes of Tao and Wu, which also try to use entropy to say things about sumset cardinalities and so on. But the first systematic effort was probably in Ruscha's paper, and then we followed that up with the work I'm going to describe now. And then about a year later, Tao wrote a paper on entropic versions of the Feynman's theorem, and he also gave entropic versions of the Balog-Semeredi-Gowers theorem and so on. I just want to mention that the focus of the Tao paper is different from the focus of our paper, because as I mentioned, we are not focusing on structural results, but more on developing the sumset calculus. And so there is some peripheral interaction, but not too much. Okay, so some terminology that we will need. Square bracket n, as usual, is the index set 1 through n. At all times, we are going to be considering either n sets or n random variables. So that's the index set. A collection C of subsets of n is a hypergraph, and the sets in C are hyperedges. Right? So for example, there's a hypergraph that's listed there. If all these sets were of size 2, you could think of them as the edges in a graph. So this is the natural generalization to sets of size larger than 2. For any index I in the index set, you define the degree of I in this hypergraph as the number of sets that contain that index. This is the natural generalization of degree from graphs to hypergraphs. And we say that a hypergraph is R regular if each index has the same degree R. Okay, so this is the same as this natural generalization of the notion of a regular graph, except that instead of edges, we have sets that might contain more than 2 elements. Okay, so we say that a set function, by the way, please stop me if anything is unclear at any point. I realize there's a lot of terminology and so on that we need to go over. So a set function G going from the class of the power set of 1 through n is submodular. A real valued set function is submodular if G evaluated at the union of S and T plus G evaluated at the intersection is at most the sum of G evaluated at the two sets. And a basic lemma, a property of submodular functions is that if a set function, I should use G, I'm going to use F for other things, but if a set function G is submodular and G evaluated at the null set is 0, that looks like an innocuous condition, but we will see later that it's not, then G is fractionally subadditive. And what that means is that I can bound G evaluated at the full set 1 through n in terms of G evaluated at subsets of an R regular hypergraph, and the coefficient that appears outside the sum is 1 over R. Okay? So the way to think about this is that if you write the indicator function of this set here, that's just the same as 1 over R times the sum of the indicator functions of the sets S. Okay, that's just a simple interchange of sums will show you that. And what this is saying is that that sort of identity for indicator functions is respected, and there's an inequality which respects that identity, and that's this fractional subadditivity. Okay, so the fact that submodular functions whose value at the null set is 0 are fractionally subadditive goes back to Bondareva and Shapley in the 60s, but it's been rediscovered again in statistical physics literature by Olenier Pinchon, and we have a survey paper which looks at extensions of these in applications in combinatorics and so on that has all the references. Okay, so here are the promised illustrative inequalities. If Z1 through Zn are independent discrete random variables taking values in an abelian group, then for any R regular hypergraph on the index set, one can it's the same, it's this fractional subadditivity inequality that I mentioned, except that the set function we are looking at is the entropy of the sum. Okay, so we consider the set function, which is the entropy for any set S, it's the entropy of the sum of the random variables indexed by S. Okay, that is fractionally subadditive. Okay. There's also a cardinality analog. Like I mentioned, the analog of entropy is the log of the cardinality. So if x1 through xn are finite subsets of an abelian group, then for any R regular hypergraph, the cardinality of the total sumset can be bounded in terms of the cardinality of the subset sums. Okay, so you take a subset of the collection of sets and you look at their sum, and those cardinalities can be used to bound the full subset cardinality. So you see that the additive form becomes a multiplicative form because of the logs. Okay, so the cardinality inequality here was conjectured by Gyarmati, Matolsky, and Rusha in 2000. Well, again, misleading dates. The paper was published in 2010, but it was circulated in 2007 or earlier. And this was proved independently by three groups, by Gyarmati, Matolsky, and Rusha themselves, by Ballester and Bolobash, and by us. So it implies, just to indicate possible applications of this, it implies, for example, the known fact, which, for example, one can find in Nathanson's book, that if you look at the k-fold sumset of A with itself, so you take A plus A k times, you look at its cardinality raised to 1 over k, this is a non-increasing sequence. And how do you see that from this cardinality inequality? Well, just set all these sets x1 through xn to be just A, and consider the R regular hypergraph, which is the collection of all sets of size n minus 1. Okay, so the collection of all sets of size n minus 1 is an n minus 1 regular hypergraph, because each index appears in n minus 1 sets, right? The n minus 1 sets that do not do not exclude that index, right? And therefore the product there, all the terms on the right hand side are just the same because the sets A are the same. So that's just raised to the n. So on the right hand side you have the power n over n minus 1, and that's exactly what you want to show. Okay, so this is a version of this monotonicity of k-fold sumsets raised to the 1 over k for different sets x1 through xn. Okay, so how are these entropy and cardinality inequality related? So let's note that one might hope to prove the cardinality inequality trivially using the entropy inequality, and the hope would be the following, from the following, that so here is an observation that for if we write xs plus for the sum of the xi's indexed by s and zs plus for the sum of the zi's indexed by s. So zs plus is a sum of random variables and hence a random variable, and xs plus is a set. Then for any s, zs plus is supported on xs plus. That's easy to see because the zi's are supported on the xi's. And therefore the entropy of zs plus is bounded by the log cardinality of xs plus. So the so the left hand side and the right hand side of the entropy inequality are bounded from above by the left hand side and the right hand side of the cardinality inequality. So what would we need to deduce the cardinality inequality from the entropy inequality? The inequality A would have to be an equality, and then one would have a chain by which you could deduce it. But the problem is that the entropy inequality holds only for independent random variables. So one would need to find a product distribution for this z1 through zn such that their sum was uniformly distributed on the range. Okay? But in general, there does not exist such a product distribution. There do exist such distributions such that the sum is uniformly distributed on the range, but they would have dependence, and then you wouldn't be able to use the entropy inequality. Okay, so even though they are analogous, the connection is not immediate, but nonetheless we will see that both the entropy and the cardinality inequalities can be proved, using entropy in rather straightforward ways. Okay, so having described some illustrative inequalities, I want to describe the more general setting out of which these inequalities fall out very easily. The more general setting we want to consider is best thought of in these terms. So for subsets of some ambient space, so x1 through xk, let's say, we will talk about functions f of x1 through xk, which is another set, which is basically you just plug in all possible values of elements of x1 through xk in there, and run it over all possible elements, and that's that set. So when the ambient space is a group, the only operations available are basically the sum or the inverse, and so all compound sets are sumsets. But if you have more structure for the ambient space, then you have correspondingly a larger class of compound sets that you can consider. So I'm not going to talk about possible applications to more structured classes of sets, but that should be, one imagines that the inequalities that I will describe should have applications in those settings. So what is a partition determined function? So the question which I want to ask is, if you have a function f that's acting on a variable number of arguments, okay, when can one relate the entropy or the cardinality of these compound sets that you get by acting a function f on variable number of arguments? So what do I mean by that? So for sums, one key point is that once you know one of the summands, if you have sum of two things, once you know one of the summands, the sum is determined by the other summand. So let's generalize this notion. So let xi be finite sets, and let me write xs. Note that xs is distinct from xs plus, which was the sum of the xi's indexed by s. Xs is the Cartesian product of the xi's. Okay, and for in order to be unambiguous, let's label the the order of the indices in the Cartesian product are in increasing order. Okay, so then q of x1 through xn is going to be the disjoint union of these. That's just ignore that. That's basically xs. So it's the disjoint union of the xs over all non-empty sets S. And and then one can describe a projection function, the natural one, from xn through any to any xs, which just yields those coordinates. Okay. So now I will say that a function f defined on q of x1 through xn is partition determined if for all n tuples x and y, so all x and y in the full product space, f evaluated at the projection on a set S and the projection on the set S complement determine f evaluated at the full n tuple. Okay. So what does that mean? If you have two x and y, if you have two n tuples x and y, and the value of f at the projections to S and the projections to S complement coincide for any S, then you know that the value of f at the for the full n tuples coincide. Okay. And we will say that a function f is strongly partition determined if for any n tuple, any two of the objects, so there are three objects here, there is f evaluated at the n tuple and f evaluated at a projection to S and f evaluated at a projection to S complement. If any two of these objects determine the third, we will say it's strongly partition determined. Okay. So let me illustrate this with an example. So for example, if n is 5 and S is the set 1, 3, 4, then let's say x is x1 through x5, xs, that is the projection of x to S, is x1, x3, suppose that's 1, 3, 5 on top. Suppose S is 1, 3, 5. Sorry, typo. So then xs is x1, x3, x5, and xs complement is x2, x4. Okay. Then so I'm just reprising the definitions here. And so examples would be, if you consider the projection function itself, so f of xs is just xs. Okay, so remember f is defined on q, so that's the disjoint union of all these Cartesian products. So it's defined on variable number of arguments. Okay, so f of xs, if that's just identity, then that's strongly partition determined because xs and xs complement determine the full n tuple. Okay, so that's trivial. And any two of them determine the third. And moreover, the sum function in an abelian group, this is the important example. That is, if I take f of xs to be the sum of the elements of x indexed by S, in an abelian group, this is strongly partition determined, because if you know the sum of x1, x3 and x5 and the sum of x2 and x4, you know the sum of all of them. And conversely, if you know the sum of all the elements of x and the sum of x1, x3, x5, you can uniquely determine the sum of x2 and x4. Okay, so sum function in an abelian group is also strongly partition determined. Okay, so here is a general entropy inequality for partition determined functions, for strongly partition determined functions. If xi are finite sets and f is any function defined on q of x1 through xn, which is strongly partition determined, and suppose z1 through zn are independent random variables taking values in x1 through xn, then if you write f sub s for f evaluated at the projection of z to the set S, okay, then the entropy of this f sub s is basically submodular. It's a submodular function. Okay, so that might be a bit much to parse. So we will look at it in a minute in the concrete setting of sumsets in abelian groups. I mean of sums in abelian groups. But let me just note for now that this general submodularity inequality immediately implies by this lemma that I mentioned, the fractional subadditivity lemma, that for any R regular hypergraph one can bound the entropy of the partition determined function applied to the full n tuple of random variables in terms of the entropy of the partition determined function applied to subsets of the random variables indexed by this that are in this hypergraph. Okay. Okay, so what does that translate to for sums? So it means that if the zi's are independent random variables taking values in a discrete or they just need to be independent discrete random variables taking values in some abelian group, and zs plus as before is the sum of the zi's indexed by S, Then G of S, which is the entropy of ZS plus, that's a set function on 1 through n, on the subsets of n. That's a submodular set function. And in particular, if n is 3, then what this means is that the entropy of Z1 plus Z2 plus Z3 plus the entropy of Z1 is bounded from above by the entropy of Z1 plus Z2 plus the entropy of Z1 plus Z3. Okay. And in particular, if you write down the fractional subadditivity consequence of this submodularity inequality, this is exactly the illustrative entropy inequality that I mentioned in the introduction. Okay, so this follows from these more general results. So I should mention that we learned from discussion on Terry Tao's blog that this submodularity of the entropy of sums is actually implicit in a paper of Kajmanovic and Vershik in 1983. That's not surprising actually, because it's a very elementary proof. But as we will see later, there are interesting extensions of this to continuous settings which do not seem to have been known before. Okay, so let me also mention cardinality inequality for partition determined functions. So here we do not need strongly partition determined, just partition determined is enough. So suppose xi are finite sets. Note that we do not need any structure here. This is completely general. F is just some function defined on Q of x1 through xn, which is partition determined. Then for any subset V of F applied to the full product set, okay, n tuples. And if we write Fs for F applied to projections to S, okay, then one can bound the cardinality of V in terms of something. So again, this might be difficult to parse when you're just looking at it like that. But the point is that if you specialize this to the case where V is the full set, if suppose F is just this sum function in an abelian group and V is the full set, so it's just the full sum set, okay, that's, this should be xn plus, not xn. So this is the sum of all the xi's, okay, on the left hand side. Then that's bounded from above by, this is what you get by using this general cardinality inequality. And this is exactly the illustrative cardinality inequality I mentioned in the introduction. So one point to note is that the sum function or the product function, if you want to write it in product form, is not partition determined in non-abelian groups, okay, because result can still be used to say things about non-abelian groups by considering a different partition determined function. Okay, so I'm going to skip over the proofs mainly because I'm not, if everyone is familiar with manipulating entropy and so on, then the proofs are very easy to describe. The proof of this general entropy inequality for strongly partition determined function is 2 slides. And the proof of the cardinality inequality is 3 slides. But in order to avoid getting into too many details and because I don't want to give too much background, I'm going to skip the proofs, but they are extremely elementary. Okay, so let me instead move on to discussing some consequences of these entropy and cardinality inequalities. So the first consequence I will discuss is entropic inequalities of Plounec-Rouchat type. So if Z0 through Zn are independent discrete random variables taking values in an abelian group, and C is an R regular hypergraph on 1 through n. Note this is a R regular hypergraph on 1 through n. So Z0 is a distinguished element, okay, which I'm going to write separately in all the sums, okay. Then one can bound from above the entropy of Z0, the entropy of all of them, Z0 plus all the Zi's, in various ways in terms of the entropy of Z0 plus Zs plus, okay. So I have not written this in the more familiar way that one is used to seeing Plounec-Rouchat inequalities. I will write it in that form in a minute. The reason I wrote it in this form is that if one writes it in this form, at least the first inequality, I can show you a proof by looking at it. And the proof is the following. Remember the illustrative entropy inequality that I described in the introduction that said that the entropy is fractionally sub-additive, right? So here, from this R regular hypergraph on 1 through n, I'm constructing a mod C. C is the original hypergraph. A mod C regular hypergraph on 0 through n. Okay, actually a multi-hypergraph, sets repeated, but nonetheless, it's a mod C regular hypergraph on 0 through n. And what is that hypergraph? For every set S in C, throw in the set S union 0. Okay, that means that every index I from 1 through n has appeared R times in this new hypergraph. Okay, but 0 has appeared mod C times, right, because it's there in each of these things. So to make each of the other elements 1 through n appear mod C times, you throw in mod C minus R copies of 1 through n, the set 1 through n. Okay, this makes it a mod C regular hypergraph. Okay, and then this first inequality here is just a trivial application of that illustrative entropy inequality that I mentioned. So the second one is also not hard, but it's slightly more subtle, and it uses the full strength of the submodularity of entropy of sums, not just the fractional subadditivity. Okay, so now let me write this in the more familiar way. So suppose you define non-negative constants beta s for each s in this hypergraph by by prescribing that the entropy of z naught plus zs plus is the entropy of z naught plus beta s. So this beta s somehow are measuring sort of expansion of z naught when you add zs plus. Okay. Then you can write these bounds in terms of the betas. Okay, and you get simple expressions. In particular, the second one is looking very much like Plunay-Krusha inequality, the traditional Plunay-Krusha inequalities. Okay, so I should mention that neither of these bounds seems a priori better than the other. They have a common weakening, but I can't see a way to that one is stronger than the other necessarily. But let's look at some specializations. So suppose you specialize to the hypergraph of singleton sets, okay, which is one regular. Then the inequalities simplify. So if you write entropy of z naught plus zi is the entropy of z naught plus beta I, then one can bound the entropy of z naught plus all of these random variables, independent random variables, in terms of the beta I. So the usual Plunay-Krusha style bound would be entropy of z naught plus the sum of the beta I. But one can also reduce the coefficient in front of the sum of the beta I to 1 over n at the cost of throwing in a 1 minus 1 over n times the entropy of zn plus. Okay, that's the first inequality. So you see that, so this last inequality that I've written here is the entropic analog of the original Plunay-Krusha inequality for different summands. And as I mentioned, it's implicit in a paper of Kaimanovich and Vershik. And I should also mention, I won't bother describing it, but the original Plunek inequality, which is slightly more general than the identical sets case of the Plunay-Krusha inequality for different summands, that also has an entropy analog, not surprisingly. Okay. So we also want to look at cardinality analogs of these general sort of Plunek style entropy inequalities. So let's see, let's just translate these inequalities here to cardinalities, and then the first inequality has a translation that we can prove. So if A and B1 through Bn are subsets of an abelian group, and C is an R regular hypergraph, and little c is some coefficient that depends on R and the size of the hypergraph, then for any D that is a subset of the sumset Bn plus, the size of A plus D can be bounded in terms of the size of D and the sizes of A plus Bs plus. Okay, so again you have all, if you know something about the sizes of these partial sumsets on the right, then you can bound the size of A plus D. And the the point about this is that you don't need to take any subset of A. This is true for the full set A. Okay, unlike the Plunek-Rusha inequality, which is true for subsets A prime of A. Okay, so special cases of this were developed in parallelly in the other papers that I mentioned that came out around the same time. So when C is the collection of singletons, this reduces to this inequality here, and this was proved for k equals 2 by Gyarmati, Matolsky, and Rusha, and for general k independently by Ballester and Bolobash. And another paper of Gyarmati, Matolsky, and Rusha proved the case of where the hypergraph C is the collection of Lie one outsets. Okay, so the question then arises: we have given an cardinality analog of the first inequality here. What about a cardinality analog of the second inequality? And there, that remains a conjecture. So for any finite sets A and B1 through Bn in an abelian group, it's not possible for the exact cardinality analog of that second entropy inequality to be true, and I'll mention the reason in a minute. But the natural conjecture here is that there is some non-empty set, a subset A prime of A, such that if you replace on the left hand side A by A prime, then you can get bounds. Okay, so let me comment on this in a minute, but before that, let me mention that that if you specialize this to singletons, the hypergraph of singletons, this is the original Plunek-Rusha, and let's write this just for n equals 2 of the B sets. This is the original Plunek-Rusha inequality for different summands. Okay, so if you have bounds k1 and k2 on these, then you have a bound on that's of the form k1, k2. Okay, and also the case of this for all sets of size m for any m less than n was proved by Gyarmati, Matolsky, and Rusha in 2008. I think actually that their method might extend to prove this more general conjecture for regular hypergraphs, but we didn't bother to do that because we think that there should be maybe simpler proofs. Their method was somewhat involved. Okay, so let me make a few observations. So there's an essential difference between the set cardinality analogs of the two entropic Plunek inequalities that I described, although the entropy versions look very similar. So indeed, while the main difference is that, in one case I could get the exact cardinality analog, whereas in the other case one needs to consider subsets A prime of A. And the reason that A prime cannot be taken to be the full set A arises from a fact observed by Rusha, that log cardinality of some sets is not submodular, even though, as we showed earlier, the log cardinality of some sets is fractionally subadditive. Okay, so on the other hand, entropy is submodular, entropy of sums is submodular, and therefore that's why there's the difference. That's explained even further by the fact that it was only for the second entropy inequality that we needed to use the full strength of the submodularity of the entropy of sums and not just the fractional subadditivity. Okay, so these insights fit in well with the recent insights from George Petridis here, from where it becomes clear that the heart of the Plunek-Rusha inequality is that there is a submodularity type inequality that is true if you replace the set A by a subset A prime of A. Okay, so whereas the lack of the submodularity of log cardinality explains why you cannot take A prime to be the full set, the fact that you can have some sort of submodularity with A replaced by A prime implies that one can say something after all. Okay, so let me move on to consequences of the general inequalities I described for non-abelian groups. So what is different here? So if A, B, and C are, how much time do I have, by the way? I have time? Yes. Okay. So if A, B, and C are finite subsets of a non-abelian group with multiplication as the group operation, then the set ABC need not have any relation with the set AC. We already talked about that. So we cannot expect the same inequalities to go through. The naive product function is not going to be partition determined. However, we can try to use the fact, which is standard when thinking about non-abelian groups, that the set ABC may be related to the sets A little bc, where this little b is some fixed element of the set B, and you can consider all these sets which are generated like this by looking at A little bc and try to somehow relate the cardinality of ABC to cardinality of these sets. Okay, so the question is, can this technology that we described of inequalities for partition determined functions be applied to non-abelian groups? And indeed they can. So the application we give is to partially resolve a conjecture of Ruscha. So the conjecture of Ruscha is about basically the non-abelian analog of the illustrative cardinality inequality in the introduction. But let me mention that we are able to resolve the special case. So suppose xi are subsets of a non-abelian group, and define aij to be so for I less than j. Okay, I and j are indices in 1 through n. For I less than j, let aij be the maximum cardinality of, you look at xi and xj at two ends and then run over all fixed elements xi plus 1 through xj minus 1 between xi and between the sets xi and xj. Okay, so this is a collection of sets that you get by running over those elements. Look at the maximum cardinality of such sets, that's aij. Okay, so this is the natural analog of what would have been just xi plus xj in the abelian setting, right? And then we can show that for any n, so this is not the version for our regular hypergraphs, but this is the version for the hypergraph of all sets of size n minus 1. So the cardinality of x1 of the full product set x1 through xn can be bounded from above in terms of the product of these aij's, which are these maximum cardinalities here. So there are two things that are needed in order to prove this. One is a non-trivial choice of a partition determined function. So namely, one can consider the following function, which is partition determined. So if S is a contiguous set, that is, it's of the form k plus 1 up to L, okay, then let f sub s of x, so f defined on on xs, right, the Cartesian product corresponding to indices in S, okay, that restriction of f to that Cartesian product is just the product as usual, xk plus 1 through xl. But otherwise, if S is not a contiguous set, just use the projection to S itself. So f defined on an S tuple, so to speak, is just that S tuple. Okay. Now this function is partition determined. It might be a product if it's contiguous elements, but the other one is not going to be in that case. But if you know both of these things, you can compute the full product, right? Okay, so that's one ingredient, is using this particular partition determined function, and the other ingredient is a new inequality for joint entropy, which basically, so I don't want to describe it because I haven't talked about conditional entropy and so on too much. But the point is that this is a strengthening of the so-called Hans inequality, which has been known for a long time, and this is a strengthening which involves somehow on one side you have the entropy of Z1 through Zn, and on the other side you say something in terms of, you look at all I less than j, all pairs ij with I less than j, and then you look at the conditional entropy of zi and zj conditioned on everything in between, on the z's in between I and j. Okay, so this is a strengthening of the usual so-called Hahn inequality, and by combining these two ingredients, we are able to prove this result, which was conjectured by Rusha. I mean, Rusha conjectured a more general version which we are not able to prove, and in fact, it does give some hints about the general conjecture, because the more general conjecture, it turns out that the corresponding entropy inequality here is so. That's what I wanted to say about the discrete setting. Let me say something about continuous analogues. So one can talk about continuous entropy in the following way. So suppose G is an abelian locally compact group and lambda is the Haar measure on G. Then if mu is a probability measure on G, which is absolutely continuous with respect to lambda, then the entropy of mu is defined in the same way as before, but we replace the probability mass function by the Radon-Nikodym derivative of mu with respect to lambda, and we take the integral using the Haar measure, or instead of the sum. So of course it specializes in the discrete case, and so let me mention that although one result that I'm going to mention holds for general abelian locally compact groups, most of what I'm going to say is going to be restricted to RD. Okay, so if X is a random vector in RD with density F, probability density function F with respect to Lebesgue measure, then the entropy of X is defined as minus the integral of F log F. And as usual, we'll abuse notation and write the entropy of X even though it just depends on the density F. But one difference from the discrete situation is that the entropy of X, first of all, may or may not exist. Second, even if it does, it takes values in the extended real line. Okay, so in particular, it may be negative, it may be minus infinity or plus infinity. So here is a continuous analog of one of the inequalities we mentioned, namely that given independent G-valued random variables on any locally compact abelian group X, Y, and Z, whose distributions are absolutely continuous with respect to Haar measure, the entropy, the continuous entropy of the sum is still submodular, provided the entropies are well defined. Okay, but the interesting thing is that even though one has the submodularity, many of the consequences of the submodularity, one has to be very careful in applying the submodularity. And the reason is that this entropy can take negative values, as I mentioned. In particular, I mentioned this fractional subadditivity lemma, which we refer to again and again, and that said that if you have a submodular function whose value at the null set is 0, then it is fractionally subadditive. But the value of this submodular function at the null set is not 0. In fact, the correct way to think about the value of this, so what's the submodular function here? The submodular function is the entropy of the sum of Zi I going I in S, right? That's the submodular function that we are looking at. So this is G of S. So G at the null set is basically the entropy. You can think of all of these as being plus 0 if you like. Okay. So G of the null set is essentially entropy of 0, and this is deterministic. This is a point mass, right? But the continuous entropy of a point mass is minus infinity. I mean, if you have, okay, so assuming, so for example in RD, this is minus infinity. Okay. So in particular, you cannot deduce fractional subadditivity from this inequality. So for example, if you set Z equals 0 in this inequality here, in the discrete case, you would have gotten as a trivial consequence the entropy of X plus Y is less than or equal to the entropy of X plus the entropy of Y, okay, whose cardinality analog is the fact that the cardinality of A plus B is bounded by the product of the cardinalities of A and B. But that's no longer true in the continuous case, because the volume of Minkowski sum is not necessarily bounded by the product of the volumes, right? Okay, so that's the point here. So some of the inequalities that we mentioned earlier go through to the continuous case. So the second entropic Plunek inequality does, but the first one and the illustrative entropy inequality that I mentioned, they do not go over to the continuous case. Okay, so some consequences of these observations for convex geometry are developed in joint work with Sergei Bobkov, and let me just briefly mention that. Again, how much time do I have?
A bit more than 5 minutes.
Okay, so one consequence is the following, that one can develop Plunek-Rusha type inequality for volumes of Minkowski sums of convex sets. This only works for convex sets. That's essential to our method of proof, and I don't believe that this is true for non-convex sets. So suppose C is an R regular hypergraph on 1 through n, okay, and we have convex sets A and B1 through Bn in Rd, okay. Then I'm using modulus for volume. So the volume of A plus this, so suppose we assume that the volume of A plus Bs plus, if you like, the sum of the Bi's indexed by S, raised to the 1 over D, this is the analog of the expansion in the earlier setting, right? This is bounded by some constant depending on S times the volume of A to the 1 over D. If we have these bounds for each S, then the volume of the full Minkowski sum A plus B1 plus B2 and so on up to Bn raised to 1 over D can be bounded from above in terms of the volume of A to the 1 over D times something involving these constants. But the new wrinkle here is that one has this additional factor of 1 plus n, which depends on the number of sets. Okay, it does not depend on dimension, but it depends on the number of sets. Okay, so this so as far as we know, these are the first inequalities of this type, upper bounds for volumes of Minkowski sums, where we do not use any non-volumetric information about these sets. Okay, and we do not invoke some affine transformation or something like that. We are not using, say, the covariant structure of the uniform distributions on A or B or anything, in which case inequalities are known. Okay, so as I mentioned, this is the additional factor is dimension independent, depends only on the number of sets. So that's one consequence, and another consequence is that if is to the so-called reverse Brun-Minkowski inequality. So this inequality says the following. It was developed by Vitaly Milman in 1986. It says that if you have two convex bodies A and B in Rd, then there is an affine volume preserving map U. So in other words, this is a linear transformation with determinant 1, such that with some absolute constant C, if you replace A by this transformed copy of A, okay, with after this affine transformation is applied, then there is a sort of reverse of the Brun-Minkowski inequality that is true. That is, one has an upper bound for the volume to the 1 over D of the Minkowski sum, and the additional factor is a constant that does not depend on dimension. Okay, so by the Brun-Minkowski inequality, one always has the reverse inequality with C equals 1. So this is why this is called the reverse Brun-Minkowski inequality. And this gives rise to the natural question, perhaps I should have mentioned that, okay, so why is it that I'm able to go between continuous entropy and volume? Because there is analogous, just like I said that the discrete entropy, which I was denoting by capital H, if X is supported on a set A, then I said that the entropy of X is bounded by the log cardinality of A with equality if and only if X is the uniformly distributed on A. Similarly, in the continuous case, the same thing holds, except that the entropy is bounded from above by the log volume of A instead of the cardinality. And again, this with equality if and only if this is the uniform distribution. Okay, so that suggests that maybe there is an entropic form of the reverse Brun-Minkowski inequality, where we replace convex sets by distributions that have some convexity property. And indeed, there is such. So what we can prove is that if x and y are independent RD valued random variables with log concave densities, this means the logarithm of the density is concave, then for some affine entropy preserving map, so entropy preserving maps are the same as volume preserving maps, basically determinant 1. The entropy power, I haven't described what the entropy power is, but the entropy power is the exponential of twice the entropy over the dimension. So this is the analog of, so the entropy power of a random variable x is the exponential of twice the entropy of x divided by dimension, and this is the analog of the volume to the 1 over d. So since the exponential of the entropy is like the volume, this is like volume to the 1 over d, and 2 is there for reasons that I don't want to go into now. So one can show that the entropy power, there is a sort of upper bound for the entropy power of a sum in terms of the entropy powers of the summands, once you allow for this entropy preserving transformation applied to one of the random vectors. And this is a reverse form of the so-called entropy power inequality due to Shannon and Stamm, just as the reverse Brun-Minkowski inequality is a reverse form of the Brun-Minkowski inequality. And furthermore, it generalizes the reverse Brun-Minkowski inequality, because if you specialize to uniform distributions on convex sets, which are log concave distributions, then you can recover, it's not immediate, but with some work one can recover the reverse Brun-Minkowski inequality. And moreover, this result here can be generalized to a larger class of measures satisfying certain convexity conditions. Again, not worth describing. Okay, so let me summarize. So we talked about some new entropy and cardinality inequalities for partition determined functions, which look like promising tools to obtain sumset estimates and so on. We resolved some conjectured sumset inequalities, just these calculus type inequalities, nothing structural. Some of this calculus extends to Minkowski sums of convex sets, but not all. One has to be careful. We presented an entropic generalization of Millman's reverse Brun-Minkowski inequality, and I hope I've managed to convince you that sumset inequalities in both these fields, additive combinatorics and convex geometry, are intimately connected to entropy inequalities, and that one can get some insight from looking at them from the entropy point of view. Thank you.
Any questions? So maybe I missed it. So in the continuous Plinay-Karuja inequality, you have this additional factor. In
Yes.
this one, did you say that it has to be there, or you're not sure?
I'm not sure actually, but I suspect something needs to be there. I don't know if this is, I doubt this is optimal.
Other questions? So, no, thanks again.
Thanks.